Okay, number 23, we have a classic related rate problem with a ladder sliding down a wall. So I chose my variables to be x, y, and z. Technically, you use any letters you want there. And so the ladder's 20 feet long. It's slipping down at 3 feet per second. And then it's asking how fast is the bottom of the ladder moving along the ground when the bottom is 16 feet from the wall. So we know the ladder length is 20. 16 will be the horizontal distance as the ladder is moving away from the wall. And your related rate equation will be a Pythagorean equation, x squared plus y squared equals z squared. And then I put over here that dy dt is -3. Always be careful that if something is decreasing, it won't show a value of negative. You have to realize that the negative is there. Slipping, or probably would have been better if it was said sliding down the wall, but it says slipping down here. So I guess that's good enough. But that's clearly negative. So related rate equation is easy. Just be 2x dx dt plus 2y dy dt equals 2z dz dt. Now, since the ladder is not changing in length, that means dz dt will be 0, and that's true for any related rate equation. If any particular variable will not be changing, it will have a rate of change of 0. Therefore, that right side's pretty much gone away. No matter what z is, that'll be 0. So we have x, which is 16. We have dx dt is what we're trying to find, that rate going across. We have dy dt, but we don't have y. But we can get that real easily by going back to our original Pythagorean equation, coming over here and solving that for y. So even after you take the related rate equation derivative, you still need that original equation. So Pythagorean theorem, real easy, that's going to be 12. So the ladder will be 12 feet high. So there's a missing value. So we have 4 variables. Solving for 1, we know 3. So 16 is x, dx dt is unknown, y is 12, dy dt is -3. Set it equals 0 from up here, and pretty easy algebra from there. So you get 2.25 feet per second, which they have rounded 2.3. No other answer is even close. I probably would have used 2 decimal places myself if I made this up, but that's all right. So that one's solved. Number 24, a right circular cylinder, which these kind of problems with it, fancy geometric formulas, I don't expect you to know those. I would give you the formula. However, you have to develop the related rate equation. So you see I gave that v equals pi r squared h. And this one's also in my notes in the related rate equation section. I did this same starting out right circular cylinder. So you got to do a product rule. I left pi factored out. So the derivative of r squared would be 2r dr dt times h plus r squared times the derivative of h, which is dh dt. Dr dt, so we have the radius is increasing at 5 inches per second, so dr dt is +5. The height is decreasing, so once again that means -3 inches per second, so it's -3. We have r is 17, we have h is 8, and it's asking at what rate is the volume changing, positive or negative, of course. If you have one decreasing, one increasing, the volume could even be staying constant theoretically. So it's asking for the volume changing, so that's how you know we're looking for dv dt. So you always have to read that carefully to make sure because you could have worded differently, could have been solving for dr dt or dh dt, but not in this particular example. So the left side is the unknown. So here's the 2 from the up here, the r is 17, dr dt is 5, h is 8, r is 17, -3, it's dh dt, plug all in there to get 493 times pi. Now keep in mind the answer did not have to have it as a reference of pi. It could have already multiplied the number by pi and then had that as the answer. But This one did not, so that's why I left it like that. So obviously this would have been over 1,500 cubic inches per second had they actually multiplied it by the value for pi. Okay, let's see. Number 25, critical values. Okay, critical values are found two ways. Taking the derivative and setting it equal to 0, and then any value which the derivative is undefined, but it is defined in the original function. Always keep in mind that critical numbers are defined in the original functions. They can't be discontinuities or anything like that. And those are going to occur when you have those rational exponents, like to the 2/3 power, 1/3 power, stuff like that. They can also occur with absolute value functions. I tend not to ask those on a final, but anywhere that the absolute value forms the V sharp, or the V or upside down V, that would be a critical number. So this one's pretty straightforward. It's a polynomial. Just take the derivative of that, which would be 27x squared minus 108x plus 81. Factor out the 27, and then it's pretty easy. So you have x squared minus 4x plus 3. So you have x minus 3, x minus 1, which will then give you the values of positive 3, positive 1, which is clearly answer C. All right. Now this one, same thing, critical values. So it's function 6x over x minus 7. So you do the quotient rule. Bottom times the derivative of the top, which is 6, minus top times the derivative of the bottom, which is 1, over the bottom squared. So you have negative 42 over x minus 7 squared. Set that equal to 0. Well, there's no way that fraction's ever going to equal 0 because the numerator is always negative 42. So this would have no critical values. 7 would be a discontinuity, not a critical value. All right, absolute extremum, absolute min and max. This one's only asking for the minimum. You know, of course, on a test, it could ask for both. So not just one or the other. So I'm going to run through the process as if you were identifying both. So the absolute extrema are going to come from one of only two places: the endpoints or any critical numbers that are in the interval. That's what's key here. So if you come up with a critical number that's not in the given interval, then you don't want to use it. So when I make my little t-chart here with xf of x, first thing I always do, and they don't have to be done in numerical order, I put my endpoints in there, negative 2 and 5. Because I know those are going to be in there for sure. Then I look to see if I get any critical numbers or not. So you take the derivative of this, you're going to get x squared minus 4x plus 3. Same derivative. Well, after you factor it out, there's a couple of problems ago. But anyway, x minus 1, x minus 3 gives you 1 and 3. Then you make the decision, do I want both of those, one of those, neither of those? Well, since the interval goes from negative 2 to 5, you would actually use both of those values because they do fit in the interval. So we will keep them both. All right, so I will test both of them. Okay. So very good. And over to the right, I have my t-chart. And put in negative 2, put in 5, put in 1 and 3. And let's see what we have here. Now you're plugging in the original function, not the derivative, remember. So use your calculator, obviously, to save you some time. And you get these values: negative 62 over 3, 8 over 3, negative 8 over 3, and negative 4. Well, just by coincidence, the minimum and the maximum occur at the endpoints. Oftentimes they occur at critical numbers. So we have negative 62 over 3 is the smallest of those four numbers, so it would be the minimum. So that's the minimum y value, but it's occurring at x equals negative 2. And had they asked for the max, it would have been at 5, because that's producing positive 8/3. All right, so that's a pretty straightforward problem, I think. As long as you pay attention to your making sure you only include critical numbers that are in your interval. And you see I use the calculator here to do my little t-chart. Number 28, we're looking for relative extrema. All right, relative extrema, we're not using intervals here. All right, relative extrema are going to occur at the critical numbers, provided, we're either going from increase to decrease or decrease to increase. So first thing you want to know is find critical numbers, if any. So we take the derivative, did the quotient rule, so I have x squared times the derivative of the top, which is 2x, minus top times x squared plus 1 times 2x, all over x squared squared, which is x to the fourth. And simplify that numerator. Be careful, the minus will affect everything over here. You'll end up with negative 2x over x to the fourth. That simplifies to negative 2 over x cubed. So you set this equal to 0, you get no critical numbers. So if you have no critical numbers, you will have no extrema. So that takes care of that problem. Now here's 29. Take the derivative. You see I factored out a 12x here from the derivative and set that equal to 0. And you have a repeated factor here of x plus 2 squared. So it might look like you were going to get 3 critical numbers, which you certainly could from a derivative being cubed. It's possible to get 3 critical numbers. But we did only get 2. We got 0. When we set 12x equal to 0, x would be 0 and negative 2. So here's a little diagram of my sign chart. Negative infinity, negative 2, negative 2 to 0, 0 to infinity. You pick a test value in each interval, plug it into the derivative, and we get, let's see, did I show it? I didn't show it here, but you just plug it right into the derivative. Negative 3 is negative, negative 1 is negative, 1 is positive. So you have decrease, decrease, increase as far as your increasing and decreasing intervals go, but you only have one extrema value because you go from decrease to increase at x equals 0. Now the answer says a relative minimum of 32 at 0. So the 0 is the x value, which that kind of has to be the only answer because there wasn't a maximum. But 32 comes from plugging 0 back into the original function. And that's what the actual y value is. So that would be like saying what, the value, the point is 0, 32, comma 32. So yes, x equals 0, y is 32, that's your minimum. There was no maximum. All right, this is a little tricky problem, but it's giving you the critical values of negative 3 and negative 1, and it's giving you a sign chart for the second derivative. That's what's key here, it's for the second derivative. And this goes back to something we learned called the second derivative test for critical numbers. And so that's in my notes. Should be in the same section with the concavity and points of inflection because it involves second derivative. Well, that rule said if you take your critical number, which critical number always comes from the first derivative, put it in the second derivative, and if it's negative, you get a max. If it's positive, you get a min. And this is where the plus and minus will guide you right here. So you see negative 1's right there separating the two intervals. In fact, that's likely to be a point of inflection there at negative 1. But negative 3 falls to the left of that, so you can see that the second derivative for negative 3 would be negative because it's over here. And then the 1 falls on the right, so its second derivative value is positive, and that's all we need to know. And this one's only asking for the local minimum, but I did both, obviously. So since 1 produced a positive second derivative, it was a minimum. And since negative 3 produced a negative second derivative, it was a max. So I answered both here, but 1 is the correct answer. X equals 1 is correct for the minimum value. 31, increasing, decreasing. All right. So you see This one is already giving you the derivative, so you have to be careful there. Watch for that, or you might, be tempted to multiply that out and then take the derivative of it. But no, it's already the derivative. Makes it easy, actually. So these critical numbers then are coming from setting that already derivative there equal to 0. So you get 3 for the first one, 4 for the second one. So there's my sign chart, creating my intervals. Negative infinity to 3, 3 to 4, 4 to infinity. I pick my test values for each interval, 0, 3.5, and 5. Plug these into the derivative, which the derivative is all we have right there. Put in the 0, you're going to get positive, you'll get 3 times 4. Put in 3.5, you're going to get negative, because you'll have a negative times a positive. Put in 5, you'll get a negative times a negative, which is positive. So we're going from increase to decrease to increase. So we're looking at answer C, where we have a decreasing in the middle interval and then increasing on both of the outside two intervals. So I think the most challenging thing about this problem was realizing that that was showing you the derivative and not the original function. Okay, 32, same thing, it's giving you the derivative here. So you set each piece equal to 0. And if x to the 1/3 equals 0, you cube both sides, you get 0. And x minus 4 equals 0, so you get 0 and 4. So here are your three intervals. Test values -1, 2, and 5. So it ends up going plus, minus, plus. And we have increase, decrease, increase when you plug the test values in. So there we go. Decreasing will be the middle interval, and then we'll have increasing on the outside intervals. So that was pretty similar to the last problem. Most likely, I don't know if I would use the derivative. Maybe I would consider using it once, but more likely I would want you to take the derivative and then do this. But it still illustrates how to use the derivative to come up with those answers. Now here's an increasing and decreasing. All right, so you take the derivative using the quotient rule, and you end up with -10 over x minus 10 squared. Now, which means when you set that equal to 0, you don't get any critical values. But remember, anytime that you're making a sign chart, whether it's a first derivative or a second derivative sign chart, you want to include two things, especially when you're talking about increasing and decreasing and concavity and all that kind of stuff. You have to include all discontinuities and all that stuff in there. So even though we don't have a critical value anywhere, I didn't draw a sign chart here, but we would have had one value and it would have been 10. So 10 would have separated into two intervals, -infinity to 10, and then 10 to positive infinity. So what I'm saying here, without actually doing the formality of a sign chart, is if you put 9 into this derivative, you're going to get negative. If you put 10 into it, you're going to get negative, which means you have two intervals of decreasing, -infinity to 10, and then 10 to infinity.